Okay, I just thought I'd do a very quick video talking about correlation and regression, just a little bit of a reminder. So, if you remember, we talked about when you've got data on a scatter diagram, being able to calculate the product moment correlation coefficient. We use letter R to stand for it. It gives us a value between -1 and +1, and it measures how the points line up. So points like this, which make a perfect straight line, would have a perfect straight line with a positive gradient, would have a value of R is 1. Downhill in a straight line would be -1, and then you've got variations of that in between. And what we can do when we've got strong correlation, either positive or negative, is we can define the line of best fit. Again, this would be given to us, or we could read it from a graph, and for some reason they use different letters to the y equals mx plus c that we're used to, and they do it the other way around. But if this is the equation of the line of best fit, it indicates that the line starts at A and has a gradient of B. So that's for data where there is a linear correlation. Remember, R is measuring how well the points line up. But we have other relationships, and we can use correlation in those relationships. Specifically, we've got exponential relationships, and I'm trying hard to avoid A's and B's because we've used A and B up here already. So, but yeah, the letters don't really matter. In each case, y and x are the variables. So here we've got an exponential relationship where we've got something which has an initial value of f and is being multiplied by g each time. So for example, 2 times 3 to the power of x. So f is our initial value, the value when x is 0. We've got to be slightly careful because those axes don't always start from 0, but if it was at 0, that would be value there. And then if the multiplier is bigger than 1, you get growth, and if it's between 0 and 1, you get decay. And here you've got a power relationship, so kx to the power of n. So for example, 2x cubed, which starts from 0, 0. I know that's a bit clumsy with the graph, but that's the key difference between these two, isn't it? This starts from f, this starts from 0. And we know that x cubed looks different in the other quadrants, but we're really interested in this quadrant here. So these are the two relationships that we often come across in in sort of science and other places, and we can use correlation with both of them. Let me remind you how we do it with the with exponential relationships firstly. So what we do is this: we say, right, we take the equation relating them. Let's refocus again. Sorry, I think I've lost my focus. There we go. Apologise for that. And we log both sides of the equation. So I've logged that and I've logged that, so it's one thing. But then I use the first log rule, to split that up. Log of AB is the same as log of A plus log B. And then I use the third log rule to bring the x out of the power. So remember, I've got variables here of y and x. I can tell it's exponential because the x is in the power here. If I look down here, those have turned into log y and x. And this looks very much like this. It's just we've got x here, so this is my A, and this is my B, and that's log G, sorry, that's my bad handwriting. So what that means is if we take this data that is in an exponential relationship and we plot it on a set of axes where we don't change the x-axis but we log the y-axis, we're going to get a straight line. And that straight line will start from log f and we'll have a gradient of log g, a plus bx. And so what that means is if we've got this graph, or if we've got this equation with those coefficients, we can work out f and g by undoing the logging, and we can therefore work out our original relationship. Let's do the same for power relationships. So we start with our equation, log both sides. We use the first log rule to split the right-hand side, third log rule to bring the n down. But remember, the variables are y and x, and this time we've got log y and log x. But again, it looks a bit like this. So this is our a, and this is our b. So that means if we have something which is has a power relationship, and we plot it on a graph where we've logged both axes, we'll get a straight line. And that straight line will start from log k, and we'll have a gradient of n. No need to do any unlogging there. And if we are given the graph, or if we're given that equation, we can work backwards to get the original relationship. So these are the two non-linear relationships that we work with in correlation, and we need to be prepared for either. So here we've logged the y-axis but not the x-axis. We do that with an exponential relationship. Here we've got a power relationship. We log both axes. Now I'll be honest with you, and I know I say this a lot, I can't remember which is which, so I will always start with this. And questions will tell you what sort of relationship we're dealing with. And they'll normally tell you that by giving you either an equation in that form or an equation in that form. And sometimes they'll start here and expect you to say what these are, but it's more common to start here with these values and get you to work back to the original equation. And in the CGP book, it doesn't do this particularly thoroughly, I have to say, but there is an example of each on page 6. So this is not your active teach, this is the CGP book. There's an example of each, so I recommend that you have a go at those. The other aspect of correlation that I'm not going to go through in the video, because I think we did it fairly thoroughly in class, is the whole idea of using hypothesis testing. And that was this idea that we've done this correlation for a sample. In this case, I've got 5 values. What can we therefore imply about the whole population? And I think that the CGP book does this pretty well, but I'm fairly sure you'll have good notes on it as well. You've got one-tailed tests where we're either testing for positive or negative correlation, and two-tailed tests where we're just testing to see whether there is correlation or not. And page 11 in the CGP book, exercise 1.4, gives you some examples of that. So hopefully that will just guide you in your revision a little bit. I look forward to seeing you back in school next week.